this is my lab 6, Magnetic Molasses. The purpose of this lab is to observe the effect of conductive tube on a bar magnet when when the magnet is dropped through the bar. In the model, this interaction uh, shows computationally. The fundamentals for this lab are Faraday's law. This states that a change in magnetic flux induces an EMF and therefore current. Magnetic field of a dipole. We use this model to find the force from the magnet on each individual ring of the tube. And then also Newton's third law, the force from the magnet on the ring must be equal and opposite to the force from the ring on the bar magnet. And then lastly, Newton's second law, the net force F equals ma determines the magnetic motion, or the magnet's motion. Overall, we found the bar magnet fell much slower in the tube than it would have normally. This is because of an upward magnetic force acting on it from the induced current in the aluminum foil. The computational model we used was closed group. This model predicted the time it would take the magnet to fall and slide through the tube and help us find the terminal velocity reached during the fall. The experiment. A bar magnet was dropped through a tube of aluminum foil and measured the time it took for it to fall through the entire tube. We repeated this a total of 5 times, and the trial results averaged out to 1.15 seconds. Here are the initial conditions were tube length of 0.4 meters, an end radius of 0.025 meters, tube thickness of 0.01, and a magnet mass of 0.025 kilograms, and the magnetic moment of 3.25 am squared. And then the system is the bar magnet and the aluminum foil tube, and the surrounding are everything else outside the whatever. And then on the right shows us dropping the magnet, and that's what the tube looked like. So here are the key parts of the code we edited. First, you can see where we defined the initial conditions of the tube with the magnet. Next, we created a function to calculate the magnetic field of the bar magnet. Then we wrote a function to calculate the change in magnetic flux through each ring as the magnet falls. In the main loop, we iterate through every ring in the tube. Inside this loop, we find that the force in each ring from the bar magnet using Newton's third law, and we know the force on the bar magnet is equal and opposite. And then as you can see on line 161, yes, right there, we add this force from every ring to find the total magnetic force on the magnet. And then we then found the net force, the magnetic force plus gravity on the bar magnet. And then finally, we use net force to update the magnet's velocity and position, completing the simulation. So here are the coding results. We can see the model of the aluminum tube on the left right there. And then as the bar magnet falls, the red and blue sections representing the induced current move with it. The model also produces a velocity time graph. From this, you can see the predicted terminal velocity was at 0.035, and then that compared to the measured average fall time, which is 1.15. Sources of error are inaccurate measurements for the magnetic moment. The foil may not completely. The foil might not be completely solid aluminum, and then the magnet could have dropped off center and gotten caught on the side. Assumptions. We assumed the bar magnet fell perfectly on axis. We assumed also that the foil tube was constructed ideally with no air pockets. What if scenarios? For the first what if scenario, if the conductor had almost zero resistivity, the induced current would become extremely large, creating a magnetic force nearly equal to the magnet's weight, and the magnet downward speed would approach zero, making it essentially float in space inside the tube. And then what if the tube had holes or slots? Ring currents couldn't form in the cut section, so those areas wouldn't create magnetic force on the magnet. With broken loops, the overall opposing force would decrease, meaning the magnet would fall faster. And in conclusion, when following the change of flux from the bar magnet induced an EMF, this current caused upward magnetic pull. The magnet fell much more slowly than free fall, reaching a final velocity of roughly 0.35 meters per second. And then, in order to visualize the induced current and estimate how long it would take the magnet to fall through an aluminum tube and determine the velocity, we were able to develop a computational model in GlowScript. Thank you. That's all.